Hello APC Mechanics students, today we'll solve the past paper of RQ 2017, exercise number 3. A uniform solid cylinder of mass 0.5 kg and radius 0.10 meters is released from rest, which means the initial speed is 0. Rolls without slipping down a 1 meter long inclined plane. Now this is very important. The moment they mention without slipping, it means that rotational motion is completely related to translational motion and is launched horizontally from a horizontal table of a height 0.75 meters. Everything is indicated on the figure. The inclined plane makes an angle 30 degrees with the horizontal. The cylinder lands on the floor a distance d away from the edge of the table as shown in the figure above. So usually, as we know that the figure is located above the text and not below, so always look above. There is a smooth transition from the inclined plane to the horizontal table, and the motion occurs with no frictional energy losses, which means we can always use the conservation of energy. The rotational inertia of a cylinder around its center is given by mr squared divided by 2, then perfect. Part A, they're asking to calculate the total kinetic energy of the cylinder as it reaches the horizontal table. Now, basically here what's happening, there is a motion from the point A to the point B. Initially, we have a gravitational potential energy. This gravitational potential energy will be completely converted to kinetic energy at the point B. But since the motion is rolling without slipping, this kinetic energy is divided into translational and rotations. But here in part A, they're asking us to calculate the total kinetic energy of the cylinder as it reaches the horizontal table. And this is done using the conservation of energy. But before doing so, we need to take the P level. So which P level we're gonna take? So either we can take the table or the floor. Here it's easier for us to take the table in order to do the complete conversion from this point to this point, since in the final position we'll be able to eliminate the gravitational potential energy. And then let me say take the P level. To be the horizontal. Through the table. Here, let me repeat myself and say that we have two options to take our P level. Either we take it through the table or through the floor. If we take it through the floor, then initially and finally we would have both a gravitational potential energy. However, if we take it only throughout the table, we will have the final state only kinetic energy. And whenever we apply kinetic energy, conservation of energy again, we can always reset our P level. And now this is because this is a big law, let me say apply conservation of energy. Which means energy initial would be equal to energy final. And energy is about being kinetic and gravitational potential energy. Now, because it's released from rest, that would be 0, and based on this wise choice through the table, that would be 0 as well. Now, the initial gravitational potential energy is given by mgh, and this is the final kinetic energy that we're interested in determining, because we need to find the total kinetic energy as it reaches the horizontal table. Then the final kinetic energy would be given by mgh. Now, what does h represent? H represents the distance from the P level to the initial position of the center of mass, which is basically given by this distance, h. Now, as you can notice that h is related to 30 by sine of the angle, then h would be given by 1 times sine 30. Then the mass is given by 0.5. And it's more convenient whenever we're solving a free response to take g to be 9.81, and h, as we have elaborated, it's given by 1 times sine 30. Now plugging that on the calculator, we're gonna find that the final kinetic energy is given by 2.45 and the SI net of energy always and forever joules. Now in part B, we need to calculate the angular velocity of the cylinder around its axis the moment it reaches the floor, and this is a very tricky exercise. The only region where we have rolling without slipping is this region. So basically, initially, the cylinder starts from here. As it reaches the bottom of the incline, it will gain some angular velocity. From this point till this point, which is basically the floor, it won't gain any additional angular velocity. For this reason, if we find the angular velocity at this point, so that would be enough. Now, how we're gonna find the angular velocity at this point? So remember that we have found the final kinetic energy at this point. Here, before I continue, let me state the angular velocity as it reaches the floor is the same at the bottom of the ramp. Why? Because since rolling without slipping stops there. Then let me repeat, if you're interested in determining the angular velocity here, so it's the same as the angular velocity here, because rolling without slipping stops here. Now we know that the final kinetic energy that we have determined explicitly here can be written as two parts given by rotational kinetic energy and translational kinetic energy. Now the thing is that we need to determine omega, but we know that because the motion is rolling without slipping, V can be converted to omega, and this can be written as half. Now I is the rotational inertia of the cylinder, which is basically given by half mr square. So we have omega square plus half m. Now V can be converted to omega, so we know that V is equal to R multiplied by omega, so V square would be R square omega square, so that would be R square omega square. Now here, what do we have? We have 1 over 4 plus half, which is basically 3 over 4, so all of that is gonna be equal to 3 over 4 mr square omega square. So what we have done is that we have related the final kinetic energy that we have calculated numerically here into omega, and now we can solve for omega. And notice that in part A and in part B, we're not asked to determine any expression. We're asked to calculate numerical values because everything is given. For that, we can say that 3 over 4 mr square omega square is equal to the kinetic energy that we have determined part A, which is 2.45. And now we're gonna solve for omega. Now this is down becomes up, and these are up become down, and we take the square root, then omega is given by the square root of 4 times 2.45 divided by 3. Now the value of the mass is given by 0.5, and the value of R is given by 0.1. Now plugging this expression on the calculator, we would have that the angular velocity at the floor, which is the same at the bottom of the ramp, is given by 25.56 radians per second. And now in part C, we need to calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. Let me repeat and state again. The rotational kinetic energy basically stops at this point, and it's given by half I omega square, and already we have determined what is omega. So first let's determine what's the rotational kinetic energy. Then K rotational is given by half I omega square, which is half I is half mr square, and that would be omega square. We have all the numerical values, then half multiplied by half multiplied by 0.5 multiplied by 0.1 to the power of 2 multiplied by omega, which is 25.56 to the power of 2. Now plugging that on the calculator, we're gonna have a value given by 0.817 joules. Now we need to find the total kinetic energy at the floor. Now let me repeat and say again, for the rotational energy, it's not important whether we specify the table or the floor, because rolling without slipping stops at this point. Now for the floor, yet we didn't determine the final kinetic energy at this point, and this again should be determined using the conservation of energy, because now if we consider this is the PE level, then the final kinetic energy will be purely kinetic, which is total, and that would at this point would be purely gravitational. So let me again apply the conservation of energy, but before we need to reset our PE level, and let me say take the PE level to be the horizontal through the floor. And because we're applying a big law, let me say apply conservation of energy. And in this case, energy initial is equal to energy final. Energy in this case is being about kinetic and potential, which is also equal to kinetic. Now this kinetic, I'm gonna name it to be the kinetic total, plus the final gravitational potential energy. Initially it was at rest, and based on our choice this is 0. Now what is the initial gravitational potential energy? I'm gonna name it to be mg capital H, and we're interested in finding the total kinetic energy. Now okay, so the total kinetic energy would be mgh. Now the mass is given by 0.5. Now g is given by 9.81, and the total height, which is basically the height from the initial point to the floor, which is 0.75, plus 1 times sine 30 that we have used previously. So 1 times sine 30 plus 0.75. Plugging that expression on the calculator, we would get a value given by 6.13 joules. Now we're ready to calculate the ratio of the rotational kinetic energy to the total kinetic energy, which is basically given by K rotational over K total. That is 0.817 joules divided by 6.13 joules. Now the units cancel, and because we're determining a ratio of same quantities, that would be a numerical value given by 0.133, which is dimensionless. So here it's important that you don't place an unit. Now in part D, they're asking us to calculate the horizontal distance C. What does D represent? D, the horizontal distance after the disk, after the solid is being projected from this point, and we know that the type of motion in this case is being projectile motion, because the table is being horizontal. Then theta is 0, which means cosine theta is 1, which means sine theta is 0. Then we can utilize the motion along the horizontal and along the vertical. We can directly start by writing that x is x0 plus v0 cosine theta t. Now x would be the distance that we're taking. Let's assume it's being launched from the origin. the initial speed would be equal to V, which is basically r omega. I will explain why. Cosine theta is 1. For this reason, the distance is given by r omega multiplied by t. Now, why the speed, the translational speed, is given by r omega? So here we're talking about the translational speed. From here to here, the table is a level surface, and basically the amount of speed here is completely related to omega, and since we have found omega, then omega is related to v by v is equal to r omega. Okay, now it's left to determine t. T can be determined by analyzing the vertical motion, which is given by y is equal to y0 plus v0 sine theta t minus half gt square. Now minus, because our positive direction is up, so everything down is negative, and we're starting from the origin. Our vertical displacement is minus 0.75 meters downward, so this should be replaced by minus 0.75, and that would be 0 because the table is horizontal, which means in this case we would have that minus 0.75 is given by minus half gt square, which means that t here, if you cancel the minus and you isolate t would be given by 2 times 0.75 divided by g, which is 9.81. Plugging that expression on the calculator, the time lapse would be given by, so let me keep it like that. Now d is given by r omega t. R is given by 0.1. The value of omega that we have determined previously is given by 25.56. And the square root of 2 times 0.75 divided by 9.81. Plugging that expression on the calculator, we're gonna find that the horizontal distance traveled by the solid cylinder is given by 0.99 meters. Now, before I proceed with the following part, let me explain something. We know that the solid is not the most inertial object as it rolls because the mass is being distributed uniformly along its shape. Now, for example, if we change the cylinder with a hoop, which is more inertial, given by mr square, what would be the difference? The more inertial the object, the more rotational energy would be generated. The less inertial the object, less rotational kinetic energy would be translated. So as this rotational inertia increases, that would increase the conversion from gravitational potential energy to rotational kinetic energy, but in total the kinetic energy will stay the same. Therefore, a sphere of the same mass and radius is now rolled down the same inclined plane. The rotational inertia of the sphere around its center is given by 2/5 mr square. So here, if you compare the sphere to the disk or the cylinder has a factor of half, which is basically 0.5, and 2/5 would be given by 0.4. which means the sphere is less inertial than the solid, which means that less rotational kinetic energy would be generated. Okay, this is the first interpretation. Now let's go through the different parts. Idea 1 is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder at the moment it reaches the floor. So basically here what they're saying that if you repeat the same experiment and replace the solid cylinder by the sphere, what is the amount of the kinetic energy of the solid cylinder, for example, compared to the sphere? In both cases that would be the same, because this kinetic energy, and we're talking about the total, would be equal to the gravitational potential energy, since they have the same mass, capital M, and since the height is the same, so basically the gravitational potential energy is the same. So let me say that would be equal to, and let me say since both have the same initial gravitational potential energy because we're talking about same mass and height, and this gravitational potential energy is being totally converted, that is converted to total kinetic energy then both have the same total kinetic energy. Now, before I go to idea 2, let me repeat again. So the more inertial the object is, the more we produce rotational kinetic energy, the less we produce translational kinetic energy. Kinetic energy in total is given by rotation plus translation. As we start gaining rotational energy, we will lose translation. As we start losing rotation, we will gain translation. So here, in idea number 2, they're telling us, is the rotational kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the kinetic energy of the cylinder at the moment it reaches the floor? So now we're pretty sure after this explanation it's less than. Why? Because simply it's less inertial. We're talking about rotation. Since the sphere has a moment of inertia or has a rotational inertia, less than that of the cylinder, then the angular velocity of the sphere will be less than when it reaches the floor than the rotational kinetic energy of the sphere will be less than when it reaches the floor. So basically, because the rotational kinetic energy of the sphere is less than, but the total kinetic energy is the same for both, which means that the sphere has a greater translational energy, which takes us the following part. Is the horizontal distance the sphere travels from the table to where it hits the floor greater than, less than, or equal to the horizontal distance the cylinder travels from the table to where it hits the floor? So we're saying that the sphere would have at this point a greater translational energy because the rotational energy is less, which means the speed, linear speed, would be greater, which means the horizontal distance would be greater. Now let me say that would be greater than, because since the sphere has a rotational inertia less than that of the disk, or less than that of the cylinder, then the linear speed of the sphere is greater at the table, which is the point of launch, which means then the sphere will cover a larger horizontal distance than that of the cylinder. And that's it for me in this video, guys. See you soon in a new one.